All right, so how do I know that my signals, especially my differential signals on a printed circuit board, are actually going to work? I can follow best practices, use a good proper PCB stack up, and any recommendations from other engineers and myself, but how do I actually know? The way I do this and verify behavior before I send anything to fabrication is verify through signal integrity software and tools. So that's why in this video, I'm going to show you how I use Allegro X and Sigrity X Aurora in my workflow to make sure my PCB signals are right the first time before I send the board out for fabrication. So let's take a look at this. This is AI PCB, and the way I verify my signals is I get an extraction of the topology of those signals. How do we do that? Well, Allegro X has this thing where you can go into an analyze workflow manager, and this capitalizes on the power of Sigrity X Aurora. There's this thing called the topology extraction workflow, and there are many other workflows here that are extremely powerful. Check out my articles that are linked somewhere around this video to access those articles and understand the different workflows. But for this one right now, we're going to do topology extraction. What this does is it looks at the electrical signals on the PCB, right? And then it can give you a model of what the behavior is based on the PCB stack up, the thickness, the dielectric in your material, in your dielectric, the copper as well, everything in the PCB. So I'm going to show you how that's done. So what I'll do is I'll select my nets. I've selected them already to be a USB differential pair on P1 USB DN and DP for negative and positive. Then I'll view the 3D geometry to make sure I've selected the correct signals. Here we've got them coming up from layer 2, well, layer 1 actually, all the way down to like layer 10. Yeah, layer 10 signal on the 12 layer PCB. And there's this via, there's the routing down here, and then it goes up through another set of vias that go out to whatever is receiving the signal. So transmitted from the left side, received on the right side. So that's fantastic. Now, once I know that that's the circuit that I am receiving, I go ahead and notice that on this signal, this P1 USB DN, I can right click, select on that. It's selected in the 3D and the 2D, and I can right click again, show element. The show element shows me that that trace, that net really is a total of 489.8 mils. That includes your via. Okay, that includes your via in that structure as well. So now that I have the right information, the right trace, I'm going to start an extraction. In extracting the topology here, this gives me all the information I need to know about the signal trace and the PCB stack up all in one neat little diagram. So that's why we have this thing. This is the connector J1 where the signal would be coming from. This sub-circuit represents the signal trace, the impedances, and all that good stuff, the vias as well, and then the U1 would be the receiving signal. Now, how does this behave? At what data rates? We are going to find out. So first, I'll double-click on here. Instead of a receiver, I'll set this as a transmitter. Then go to my setup analysis options, and let's say this is supposed to carry USB 2.0. I'm going to set it to 0.480 gigabits per second, which is the 480 megabits per second from USB 2.0 protocol. And let's see if this handles that signal well. To do that, I'll just go my system workflow, start transient analysis, and boom, there we go. This is showing me the overall differential signal. So let me show you how this is pieced together. We have the signal minus and then signal plus overlapped on top of each other. Now, if I got the minus and plus wrong, don't sue me, okay? But you get the idea. And then their overall signal will look like this. Now, what we really want is this thing called the eye diagram. The eye diagram is going to reveal things like jitter and the likeliness of our violating bit error rate, or what our bit error rate even is. So what that is if, say, every 1 million transitions of a signal on a trace, or 1 billion transitions, 10 to the 9, 10 to the 15, or what have you, if you have any kind of droop or error or undefined state, that counts as a bit error, especially for that communication protocol. So whether it's USB 2.0, USB 3, you need to adhere to that. To meet that standard, you need to have a bit error rate below whatever the standard is. Ideally, 0, so you never even have to deal with managing that. So let's go ahead and see what these eye diagram looks like. This is something that you would see like on a time domain reflectometer, because the time domain reflectometer would set out a stimulus pattern to see what the output is going to look like. Here we have 1 0 1 0 1 0. You could even set this to whatever. I'm going to leave it as is. Okay, the eye diagram shows us, boom, there's a bit of drift over however many hundreds or thousands of measurements. You can get this on your oscilloscope as well. This gives you a statistical analysis visually of how close your trace and how clean your signals are, essentially. You can even set your or define your eye mask. There's a mask that you have to adhere to or be outside of in order to meet the standard. Now I know that as the way I've routed these traces, they meet USB 2.0 standard at this data rate. Now, with that being said, let's say I'm curious about higher data rates going through here. Can I use a USB 3.2 Gen 2X1 protocol on this thing? Let's find out. So let's say you want to run 5 gigabits per second through here. Matter of fact, 1 gigabits per second, just to start off with. Let's see if we run the simulation again. Eye diagram shows, hey, there's a bit more variation or jitter, but we still maybe kind of meet that eye performance. Well, what about 5 gigabits per second? What about 5 gigabits per second? Is it? See, no, not suitable. The eye totally collapses, probably way before then, maybe at 2.5 gigabits per second or what have you. That means this would not be suitable, or at least if you want to run a signal through there, you may need to use no vias on the circuit or whatever the case is. All right. So this is why I use this in my workflow. I don't have to do second guessing. Now there's another thing. Sometimes if you send a certain bit stream through a PCB on these little rare occasions, you could get bit streams that break the circuit operation in your PCB. Why is that? Well, you can test for that. And why that is due to a number of reasons for power and signal integrity and energy delivery and communication and whatnot. We're going to enter that signal. And let's say that is at 1 gigabits per second. Actually, 480 megabits per second. Let's go with 0.480. And then we run that simulation. It still does well for that bit pattern. Fantastic. Okay. So this is how I used my software to verify things that I just wouldn't be able to know otherwise without simulation. Okay, so you now have a physical picture or idea of how the signal is routed through the PCB through those two vias. You can see every trace segment, every via transition, every layer change, and they all matter. They're all included in the simulation process. This is truly the starting point of all signal integrity analysis. This is how I start my signal integrity analysis without having to be a dedicated signal integrity expert. In other videos in this series that I'm doing and putting together for you, I'll compare two different circuit topologies or the same topology, but with like some modifications, which basically is two different topologies. And we're going to compare the two. This is the process I use to make sure I get first time right design, and I'm passing this on to you so you can get the same. Thanks so much for watching this video. I'll see you in the next one. Peace.